Hello. Well, we're starting a new chapter today. For a while, we'll be going around in circles. Yes, this whole chapter will be on circles. So, the first thing we probably got to understand is the components. I guess you could call these components of a circle, although it's probably not the right word to use. Most of these lines here are not actually part of a circle. They don't make any sense without a circle. I can tell you that. A diameter without a circle doesn't mean much. Neither does a tangent, or a chord, or a radius, or a secant. They all require circles, or they don't have any meaning. So let's take these pieces one at a time. Probably the most common measure of a circle would be the diameter or the radius. Probably most people are even more familiar with the diameter. That is just the straight distance across. And it passes through the center of the circle. If it doesn't pass through the center, then it's a chord. A line that connects 2 points which lie on the circle. That's a chord. So this diameter is actually a chord, but it's a special chord. It's one that runs through the center of the circle. And it connects these 2 points on the actual circle. This chord here is related to a secant in the sense that they're very similar. If you were just to extend this chord so that it wasn't a segment anymore and it was a line, well, then you'd have a secant. If it goes right through the circle, intersecting at 2 points, that's a secant. If it stops at the circumference, that's a chord. Well, what about this one? This does intersect the circle, but at exactly 1 point. It's kind of like if you took this secant and kept moving it out until it only touched at 1 point. Then it would become a tangent. So this blue line here, this is the tangent to the circle, and that 1 point where it touches the circle, that's called the point of tangency. Okay, so you just need to know these terms so that when we talk, you know what we're talking about. Like always. Well, we've seen what tangents are. This line here is a tangent to this circle. It's also a tangent to this circle. Is there a special name for that? When a line is tangent to 2 circles? Naturally, there is. It's called a common tangent, meaning it's common to both circles. Doesn't mean common like it's not special or it's ordinary. It means it's common to 2 different circles. These circles, which are just touching, and touching at 1 point, have 3 common tangents. We can draw this line here, which will be tangent to this circle and this circle. We've got this common tangent and the one that runs right through. Because if these circles touch at exactly 1 point, that's what this diagram is intended to imply. Then we can run a tangent that touches at that 1 point right here. So this is actually a common tangent also. This is the only way you can get this kind of common tangent. Normally, common tangents look more like this. For instance, if I took this circle and pushed it off to the left, so it was inside the circle a bit, this vertical common tangent would not exist. Same thing if I moved this circle away, so that there was some separation. This would not exist, although we could tilt it. Maybe I should show you that. This is what I meant. If we separated these circles, now we've got 2 common tangents in the center here. And we still have these 2 common tangents. We could still run them. It gets a little crowded, but we could run a tangent this way and across this way. when they're touching here, these two circles just touching at one point might remind you of something, especially if you're into mechanics. Kind of looks like two gears meshed together, doesn't it? The relative circumference of these, well, I shouldn't be talking about that yet. Technically, we haven't learned that stuff yet. But radius we have. So the relative radius, that would be the distance from the center to here, or the diameter. That would be the, in this case, we could think of the diameter as the height of the circle from here to here. And then there's a diameter from here to here. Well, these two diameters are going to determine the slope of this line, this common tangent, when we put them right next to each other. When you get to science class, or maybe you're studying it now, when you start learning about gear ratios, I think you might find that there's a relationship between the slope of this tangent and the gear ratio of these two. Conversely, you could also find a relationship between the angle at which the two common tangents meet and the gear ratio. We're not going to go into that because this isn't a physics class. But I bet there are some people listening right now who are scratching their head wondering how to do that. And I can tell you right now that you have the information you need to do that. If you know about gears and how to figure out the ratios, then you could figure out how to apply that to the slope or the angle at which these lines meet. In other words, a different way to determine the gear ratio. You would have to make certain assumptions. For instance, the teeth would have to be equidistant on both circles. But right now, all that's important is that you know that a common tangent is one that's tangent to two circles. And if it's not obvious, if this circle were moved off to the left so it was entirely inside this circle, there would be no common tangents. This circle could overlap this one. We could push it off to the left and we'd still have tangents like this. And when I was speculating about gear ratios, that's only going to be true if the two circles touch at one point. If this overlaps, well, if you know anything about gears, you know that gears don't really slide inside another one. They just touch at one point. And if they're separate, well, that's another problem. If you've ever tried to start a car with teeth on a gear missing, you've found that all the thing does is spin around. Well, that's what happens if you separate this a little bit. One or the other may spin, but it's not going to have any effect on the other one, so there is no real gearing taking place, is there? Now when you look at all these parts of a circle, components, accessories to a circle, this is the circle here. I guess everything else is an accessory. Or you could call it a property, I suppose. I kind of like to accessorize my circles. What do you want to bet? We've got a whole bunch of theorems about all these accessories, about the radii and the tangents and the diameters, and later on we'll have circumference and area too. Well, you'd win that bet. We do have some theorems about that stuff. And here's the first one. We have a radius here. This is the center of the circle, I guess. Usually I'm just eyeballing this, so if you were to measure this and find that I was a millimeter off, I'm sorry. Here's the radius, and here's a tangent. Now, the theorem is, at the point of tangency, the radius is perpendicular to the tangent, and vice versa, of course. Well, why the heck would that be true? Well, let's see here. The point of tangency is on the circle. The distance from any point on the circle to the center is in fact this radius here, r. Radius, the word itself, is used to refer to the segment. It also refers to the length. We don't always say length of radius. We usually say the radius is 10, or say if this were A and this were B, we could say radius AB. Radius frequently refers to both the measure of the segment and the segment itself. You know from context what's being referred to. So this radius here is the distance, and by definition the distance is the shortest distance. We got this straight segment here from this point on the circle to the center, which has length equal to r radius. What is the distance from a point to a line? Remember, we studied that earlier. Would be this. Say the length of this line here. Would that be the distance from this point to this line? Nope. We've defined the distance to be the perpendicular distance from the tangent to this point right here. This tangent is just a line, so the perpendicular distance from a point to a line, the distance from a point to a line is the length of the perpendicular segment which connects the point and the line. So the distance from the center to the point of tangency is r. It's the shortest. It's when we defined, if this were not the center of a circle and just some old point, and this were just some ordinary line, the distance from the point to the line would be this perpendicular segment from the point to the line. But what is this perpendicular segment? Well, that's the radius, because the point we're concerned with is on the circle. So, radius and tangent are always going to be perpendicular. And that's useful because we've got something else to show about tangents here. Suppose we have a point outside of the circle. It's not on the circle, it's not interior to the circle. It'll be outside the circle. And we draw two tangent lines from this point. One tangent here. They have to be from the same point now. And another one, so that we have two tangent points here. This is tangent point B, and this is tangent point C. Guess what? AC, yeah, put it over here, I guess. Segment AC is congruent to segment AB. Why would that be true? Well, I can show it in just a minute, but one thing you might think about is the symmetry of this situation. We just talked about symmetry in the last chapter. As long as we did, we might as well use it. What's the rotational symmetry of this circle? Can you put a number on it? I don't think so. I don't think it matters how you rotate this circle. Any degree, any fraction of degree, any amount of degrees, you will always end up with exactly the same thing. In other words, this circle has infinite rotational symmetry. Another way of looking at that is if you have suppose you had a rectangle. Can you tell where you are on that rectangle? If you're out here somewhere, anywhere out here, can you tell just by looking at the rectangle where you are? Pretty much. If you're over here. One thing you can't do, if you're over here, say, you don't really know if you're here or you're here. You can't be too positive about, well, maybe I'm wrong about that. Let's see, off to the left. Yeah, that's right. You look off to your left and you see a corner a certain distance away. to your right, you see this corner, and then a straight line. If you were here, you would see off to the right, same distance, a corner off to your left, the same distance, and this line. On the other hand, if you were over here, you would definitely know that you moved, because this doesn't look the same at all. If you were walking around a circle, suppose it was dark everywhere, and all you could see was a circle. There was like some circle of light there, and that was it. How would you know where you were on that circle? Let's assume there are no markings on here, nothing but this circle. You see, with other irregular objects, or less regular than circles anyway, you got a pretty good idea where you are at certain points, at least within reason. For instance, if you had a square, every side's the same, but there are 4 places you could stand, and you wouldn't really know where you were for sure. You get what I mean? If this, I'll pretend that's a square. Now, if you were here, or here, or here, or here, if all you could see was this square, how would you know which point you were standing on? The answer is you wouldn't. There's no way for you to know. That's because it has symmetry in those directions. You could rotate this 90 degrees, so if you move 90 degrees, you can't tell. We're talking about relative motion in a sense here. Whether the square rotates 90 degrees or you move 90 degrees, the effect is the same. With this, if you were to walk around this circle, you would never know, and never have any way to determine which part of the circle you were staring at. Which means when you draw a line from this point to a point of tangency here, if you were to move and do it again, so you move out on the circle the same, you couldn't tell one tangent line from another. Which means that if you stay in one place and draw another one, how could you tell which tangent line you drew? Another way to look at it would be like this. What I did was I took this part right here and flipped it vertically. In other words, I reflected it about this line here, connecting the center with this point. And this point here is not on a perfect horizontal line with this point, so when I flipped it vertically, you can see where some things didn't quite match up. That's my fault. The drawing just was less than perfect. But when I flip this, everything matches up pretty much the same. Well, one reason for that is that the symmetry of the circle. But there's another better reason for that, and I'll show you right now. Just a minute ago, we showed that, I guess I should draw in a radius first. Both of these radii will intersect at 90 degrees to the tangent at the point of tangency. So, here we have 2 right angles here. Well, that's interesting. What does this look like? Well, let's not worry too much about it. The next thing we can do is draw a line from A to the center of this circle. Unfortunately, I already used C, so I guess I'll have to call the center of the circle Y. How's that sound? Well then, now that I've done this, I drew this line in here. I just created 2 triangles, didn't I? It's a triangle created by this line I drew here from A to the center of the circle. Well, that turns out to be an hypotenuse, because these 2 triangles, this is a right angle here, so this is a right triangle, and this is a right angle, so we've created a right triangle from the radii, the tangent, and then a line from the exterior point to the center of the circle. Why would we want to do that? Well, with a right angle, with a right triangle, showing congruence is a lot easier. For instance, in this case, we have our hypotenuse leg theorem. CY and BY have to be congruent because they're both radii. They're both a radius of the circle. So they have to have the same length. No way around that. On the other hand, AY is of course congruent to itself. So we have the leg is congruent to this leg, and the hypotenuse of course is congruent to itself, which means this triangle here is congruent to this triangle. Well, that means we're pretty much done, because congruent parts of congruent triangles, corresponding parts of congruent triangles are congruent, which means this leg right here, which corresponds to this leg right here, they have to be congruent. Hence, AC is congruent to AB. Pretty simple, but it'll get used, I believe. Well, this is good. We got a lot of new terms here, so let's review them and match them all up and make sure we understand what everything is. Then we'll be experts. What's B? Well, let's see here. It's right here. Well, it certainly looks like a point of tangency to me, doesn't it? It looks like we've got a tangent here that touches right there. So I'm going with G on this one. I'll say B is the point of tangency, and well, these seem to match up 1 to 1. So I hope I'm not messing up. I'm going to start crossing each out that we use. That way we have fewer to choose from. Although I probably shouldn't do it that way. I think I'll just cross out the letter, that way you can still see what it says. Okay, what's the line? BH. Well, that's tangent, but it looks like a common tangent, doesn't it? Let's see if that's one of the choices up here. Ah, common tangent. So I'd say BH is a common tangent. So that's choice H. What about AB? Remember, with this little just line, nothing else, that means segment AB. This right here means line AB. And if we put just one tail on this side, that would mean ray AB, usually. Although vector AB is frequently written that way also. Sorry. That notation isn't that weird, because frequently we write vectors starting at the origin here and going out like that. So writing AB with a little arrow over it, oh, just one arrow, not two, actually makes sense, because rays and vectors, they have a lot in common if you start them at the origin. What about, oh, that's what I was just trying to find, AB. Well, I say that's the chord, because it means segment AB. Otherwise, it would be a secant, but that would be the line AB. Oh, well, that's the next question. This means line AB, and what's that? That is a secant. What about the line AE? Well, that's a tangent line. Yeah, it looks to me like F would be the right answer there. It's not a common tangent. It's only tangent to one circle. Well, what about G? Well, G looks like the center of this circle. Oh, that was our first choice. Okay. CD. C is the center of the circle. D is on the circle. That segment that connects the center with any point on the circle is a radius. Well, there's only one choice left over. BD. And we have a chord. This is a chord, just like AB is a chord, but it goes through the center of the circle. A chord which contains the center of the circle is a diameter, D. So there we go. These are all important terms to know. Every one of these. It's brilliant the way they listed them here, because these are going to be very important for the rest of the chapter. You need to know all this. So once again, you have to open your brain and stuff some new words into it. Well, once again, it looks like our politicians, Inseam and Fleabite, not satisfied with destroying social order, are now taking a hand at geometry. Let's see how bad they can mess up geometry for us. They say that the length of the secant, AB, which has the segment symbol over it, meaning not a line, is 6. Well, a lot of things wrong with that. A secant is a line, and a line, well, you don't have a length for lines, we have lengths for segments. But they drew it, the symbol, right. This means segment AB is 6, so if you didn't say secant, if you said chord, or if you just did what politicians are completely incapable of doing and just shut your mouth and not say anything and just say the length of AB is 6, you'd be right, because you got the right symbol up here on top. If you're going to say anything, say chord. But, Abraham Lincoln explained that one. It's better to keep quiet and be thought a fool. A fool? No, not a fool. A fool. Keep quiet and be thought a fool, or open your mouth and remove all doubt. Well, say as little as possible. Say enough to answer the question, but no more. Because if you say more, even though it was extraneous and not necessary, you'll still lose credit for saying something wrong. Actually, that's probably true in life as well as mathematics. This problem brings up an interesting point. I'm kind of stupid. I explained to you that the radius is always perpendicular to a tangent. I think I forgot to mention that it goes both ways. It's an if and only if. So, if you have a line which touches the circle at one point and is perpendicular to the radius, then you have a tangent. It goes both ways. I don't think I said that when I showed you the theorem and showed why it was true. The radius is definitely perpendicular to the tangent. Conversely, if you find a line which touches the circle at one point and is perpendicular to the radius, it is definitely a tangent. It's only important now because they're asking you if AB is a tangent, and there's hardly any other way you could know for sure. I mean, you can look at it and say, well, it looks like it just touches at one point, but you can't see the rest of it, and even if you could, I mean, the lines are kind of thick. For instance, if you think back to the circles I drew, well, it looks like it kind of touches at more than one point, I think. Let me take a look here. Yeah, the reality of, an actual tangent trying to intersect a circle at only one point is kind of tough, because remember, a point has no width or length. Lines have length but no width. That's in mathematics. Unfortunately, real lines have to have width or you couldn't see them. So that when we draw them, it kind of looks like it's more than one point, doesn't it? That's why it's really hard to eyeball whether something is a tangent or not, but at least, especially when you can't see the rest of the line here. So I would say that if AB is perpendicular to AC, then AB is a tangent. How do we know if this is the right angle? Well, we just have to know if it satisfies Pythagoras' theorem. Remember, Pythagoras' theorem is another one of those things that goes both ways. The sum of the squares of the two legs equals the square of the hypotenuse. Conversely, if you have a triangle such that the sum of the squares of two sides equals the square of the other side, then you have a right triangle. Whether you wanted one or not, you're stuck with it. And this one, you should be able to tell right off it's a right angle. Remember, this is our 3, 4, 5 triangle. 3 squared is 9, 4 squared is 16. 16 and 9 is 25. 5 squared is 25. So the answer is yes, indeed. This is a tangent because this is a right triangle. Therefore, this is a right angle. Don't forget your 3, 4, 5, or multiples. Remember, this could have been 6, 8, 10, 9, 12, 15. 3, 4, 5, or any multiple of 3, 4, 5. Yeah, it behooves you to spot them quickly, because they'll probably be on the test, and not having to mess around with any arithmetic will save you lots of time. And 3, 4, 5 pops up a lot too. I think they'll kind of expect you to remember it so that you can save time on the test. Now on this one, we're given that B and D are points of tangency, meaning that these lines actually continue off that way and only intersect the circle at one point. What do we know about tangent lines which originate from the same point outside the circle? Well, just a few minutes ago, I think we showed that they were congruent, didn't we? Which means that we could solve for x and actually find the length of these. And in fact, if we didn't know that these were equal, don't see how you can solve for x, because you just got two separate equations in x that don't really mean much of anything. They're not equal to anything. You just put y equals 3x plus 10 and graph a line, I suppose. But other than that, you really wouldn't have much to work with. But since we know that these two lines have to be equal, now we got something we can work with. We can write that 3x plus 10 is 7x is equal to 7x minus 6. So this is, if I add 6 to each side, I get 16 over here, subtract 3x, and I get 4x. And I think that will lead to x equals 4. Or 12 plus 10 is 22, I think. It's 28 minus 6, and that's 22. So it works. The only key to this problem really was remembering that when you have a point outside the circle and draw two tangents from that point, the distance from that point to the point of tangency is going to be the same for both. Yeah, here we have a problem with two circles. They touch at one point. Those are also called tangent circles, meaning they touch at one point, as opposed to a tangent line, which touches the circle at one point. And RS is the common tangent, and they want us to find the length of RS. Well, how could we do that? Well, I think that if we were to draw a line from Q to S, we could figure out the length of that line, because what I've done here is drawn a radius, another radius from here to the circle, which of course has to have the same length. And it goes from the center to the point where the other circle is tangent. Over here I drew a radius from the center of this circle to the point where the other circle is tangent. Well, they form a straight line with the sum of 5 and 3, which is 8. So, if I draw this line here, I'll have a right triangle. Up here. This part will be a right triangle. This, let's see here. Okay, it was getting kind of messy. Let's start over. What we have is, we've got a right angle here, right? And a right angle over here. The line that connects these two, well, there's no reason to think that this would form a right angle or this would form a right angle. it wouldn't. But we have two right angles here. Well, and we have two lines which are perpendicular to the same line, which means that they're parallel. We're really close to a parallelogram here if we had a line like this right down here. Suppose I finish off this. When I connected these two radii, this is 5. Oops. And this is 3. The two circles touch at that one point, so I draw a radius from the center to the point of tangency of the circle, and another radius to the point of circle tangency. So this has to have a length of 8. Problem is, it's not parallel to this, so we can't just say this is 8, because we don't actually have a parallelogram. At least not yet. But suppose I were to complete this. In other words, these two lines, or segments, are parallel. Suppose I extend this so that I draw a line. In other words, I'm going to draw a line which is perpendicular to this line. And then it'll be perpendicular to this line as well, because they're parallel. Where will it meet? Well, I'm going to draw a straight line. I mean, a line perpendicular off of this line to this one. Now, this is 3 units and this is 5, so the difference here, the leg of this thing, would be 2. What we're trying to find is this, because if I complete this parallelogram with this line here and figure out what this is, then it has to be the same as this. That's how it works with a parallelogram. I'll have a 90-degree angle here and a 90-degree angle here. I just have to figure out what this is. Well, this is one leg of a right triangle. This is a right triangle. This leg is 2. This hypotenuse is 8. So we have that 8 squared equals 2 squared plus, and it's called L squared. That's this length here. Well then, we must have that L squared equals 8 squared minus 2 squared, which is 64 minus, gee whiz, I don't write very well, 64 minus 4, or 60. So L would be the square root of 60 yeah, and that's 4 times 15, right? So 2 times the square root of 15. That's L. But when I completed this, and this is a right angle here, and this is a right angle, that means RS has to be the same as our L down here, which is 2 times the square root of 15. When I started this problem, my obvious mistake was looking for right triangles, which I could find the hypotenuse of. Maybe I should say of which I could find the hypotenuse. When I was looking at the interior of this, all I had to do was create a right triangle down here, which is an extension of what is almost a parallelogram. I've got 2 parallel sides here. If I could extend this so that this was parallel to this, and we would know it was parallel if it was perpendicular to these two, then I could just find the length of this leg, and that'll have to be the same as this. Now, what I'm trying to say is I made it more complicated than it was. Sorry. Well, here's a simple question. When will 2 lines tangent to the same circle not intersect? Well, the simple answer would be when they're parallel. Okay, all done. Goodbye. I don't think that's exactly what they're looking for, although that's part of the answer. When do 2 lines not intersect? Well, by definition, that means that they're parallel. And suppose we draw the diameter. Now, a diameter, aside from being a chord which passes through the center of the circle, can also be seen as 2 separate radii. This is R, you get a radii from here to the circle, and then this radius from the center to the circle. tangent lines are perpendicular to the radii. And two lines perpendicular to the same line are parallel. So, if we had a tangent line here, and a tangent line here, well, they would both be perpendicular to the same line, therefore parallel, and they would never intersect. So, the answer is, when the points of tangent C are the opposite ends of a diameter, those two tangents will be parallel and never intersect. Now here's one where we can use our theorem that says that tangents from a point outside the circle have to be equal. I think we even proved that one. Well, if this is 12, I think that's what they say, yeah. And this is 8 over here. Well, if we remember the incenter, that's the center of the inscribed circle, that's where all the angle bisectors meet. Well, this one angle bisector, since this is an isosceles triangle, is also the perpendicular bisector of the segment. The fact that it's perpendicular isn't too important right now. The fact that it's a bisector is. Which means right here at the point of tangent C separates this into 4 and 4. Well, tangents from an outside point have to be congruent. If this one's 4, these two tangents from point C, then this has to be 4. And if this is 4, then this one has to also be 4. This whole thing is 12, which means this must be 8. And this must be 8. So we have FA, this short part here, or this section is 8. This part is 4 all the way around, right? Well, I redrew it here. Actually, it's pointed up. It seems easier to work with that way. What's going to happen if we draw a line straight from D to F? That's right at the point that breaks this side up into 4 and 8. That is to say, it breaks it up into 1/3 and 2/3. Well, that'll do exactly the same thing for the altitude here, won't it? That may come in handy later. And can we compute the altitude here? Yes, we can. Remember, the angle bisector, the perpendicular bisector, and the altitude for this isosceles triangle are all the same thing. And we can definitely compute the altitude of this, and we're probably going to need it, so let's do that right now. What would the altitude be? And let's say it's, we'll call it L. Got too many A's floating around usually anyway. That L is going to be one leg of a right triangle. 4 would be the other, and the side of length 12, that's CA, that would be the hypotenuse. So we've got that L squared plus 4 squared equals 12 squared. So for the altitude here, we get that it's 12 squared is 144, 4 squared is 16, so we get 128 here, and of course L would be the square root of 128. That's our altitude. We're going to need a lot more than that before we're done, though. Let's mark some of that off over here. If I label all of this, which I just did, I draw this line. This is parallel because we have an isosceles triangle. And right at the cutoff, this is the point of tangency of the circle. I didn't draw the circle in because things are going to get kind of crowded, and the circle doesn't add too much right now. Just remember that from here to here, in fact I'll draw that in, even without drawing the circle. We know that this is the radius. Here's the center of the circle. And D and F are the points of tangency, right where the circle touches the triangle. So this point right here was on the circle also, and so was point E. This right here was on the circle, and so was this. Other than that, we don't need to draw the circle. So what do we do now? What about the length of this thing here? DF. Well, remember when we break things up in proportions, the proportions are retained. For instance, the altitude, the straight angle bisector, or the perpendicular bisector, this straight line that goes from E to A, segment actually, that segment is 2/3 down, right? This breaks it up into thirds. We got 1/3 here and 2/3 here. That means that this line, the altitude is broken up the same way. We have 2/3 of the altitude up here and 1/3 down here. This line is 2/3 of the line to which it's parallel. Remember that from the, we started with the mid-segment theorem and showed that if we found the midpoint of this and the midpoint here and connected them, that line would be parallel. Because this is isosceles, that line would be parallel and would have the same proportion with respect to this line as the cut point did with respect to this line. In other words, we've cut this into 2/3 and 1/3. So we do the same thing with this, and this line here is 2/3 of this line, which is 8. So I guess we can write, maybe we got to put it over here to not clutter things up too much. So we've got the DF, that's this here, is 2/3 of 8. Or 16/3. Okay, so what? Well, we're just putting in things that we can figure out right now. So we're going to have to do something to figure out what the heck R is, and we're going to have to use our known values. So I'm sketching them in now. So what can we figure out from this? Let's see here. We've got this one. Now I've drawn in a little right triangle we're going to take a look at first. What good will that do? Well, we'll get there. What we're going to end up using is something from our similar right triangles. Remember, if we start with the right triangle and then drop an altitude from the hypotenuse to the opposite side, to the opposite vertex, which would be the one forming the right angle. When we do that, we produce 3 similar right triangles, the original one plus the 2 that we created when we split the first one. Well, it's those similar triangles we're going to use and the ratios to arrive at the length of our yellow line here, which is R. Don't believe it? Well, I don't blame you. Doesn't look like it's going to work right off the bat here, but we'll see. What is EF? Well, we've got this right here. And remember, since this is an angle bisector, it bisects this. But if we draw this line here, we just created another isosceles triangle. Just a little shorter than the original one. So this altitude here still bisects DF, just like it bisects BG. Who cares? Well, the reason for that is that we need to know that is that DF, we already decided, is 16/3. That means this half right here would have to be 8/3. And this part here we can figure out because, again, this is 2/3 and this is 1/3. And we worked out the altitude over here. So this side here is, I didn't put a letter here. Let's see if I got room to write it. Square root of 128. Well, looks to me like we got pretty much everything we need. 8 over 3 squared plus root 128 over 3 squared will be the square of EF. So let's do it and see what we get. Here's 8 over 3. Don't get those confused. In fact. And so, after some boring arithmetic, we take 8 over 3 squared, root 128 over 3 squared, and get 64 plus 128 over 9. 8 squared is 64. Square root of 128 squared is, of course, 128. We add them up and get 192 over 9 and take the square root of that. Now, we could reduce this, but it's going to be used in other calculations. We might as well just leave it for now, and we'll reduce everything later. Now let's take a look at what we've got. I added an extra line in here. I'm going to explain that in a second. We know this length here. We know this one. And we figured out EF. This was a right triangle. However, if I draw a line from here to here, what I now have is the two diagonals of a kite. Why? Well, in the first place, I drew it wrong. Hold on a minute. As I was saying, I now have the diagonals of a kite. Why is that true? It may not look like it, and if it doesn't, the yellow and blue here might produce something of an optical illusion, or it could be that I just didn't quite get the proportions right when I drew this. But the fact is, this is a kite. Why? Well, this is R, and this is R. So this part that I'm outlining with the pencil right here, this is 4, and this is 4. This we don't know, but it's R, and this is R. So these two adjacent sides are congruent. These two adjacent sides are congruent. So we have a kite. Why do we care? Well, with a kite, the diagonals are perpendicular. That was, I forget the name of the theorem, but that was back when we studied kites. We found that these diagonals are perpendicular. Why does that matter? Well, let's see what we have here. This is a radius, pardon me. And AC here is the point of tangency of the original circle, which means this radius has to be perpendicular to AC. It's getting a little crowded, so I didn't draw the perpendicular symbol in here, but it is perpendicular. So we had a right angle here, which we haven't really computed yet. We have this right angle, which we did compute. But notice what this looks like here. Our original, we treat this as our original right angle, which we haven't actually computed. This is 4. This is R, which we don't know yet. And this, we haven't quite figured out yet either, but we can get part of it. Because we know what this is, and we know what this is, so we can compute this part here. Because we have a right angle here. So I'm going to call this part here N, because it's knowable. That's N for no. Yeah, well, I know K starts with, I know. You don't spell no with an N. But I didn't feel like using K. Now this part gets complicated. Since this is perpendicular, what we have here is the perpendicular distance from the opposite side to the right angle. So what did we do here? We just produced a whole set of similar right triangles. There's the first one that includes the radius FC and then CP, and then there's the one we create when we cut it here. we know this is a perpendicular line because it's one of the diagonals of a kite. That's why this works. So now what we need to do in order to understand what the heck's going on, because I find it very confusing to have all these, this is the side of one and the hypotenuse of another, and on and on and on. It gets really almost annoying. So we'll do what we did last time in the previous section, is we'll draw all three triangles down here and see what kind of ratios we can come up with that might lead to a solution. So I redrew the triangles up here. A little bit confusing, but what can we do? The first big one, now put CF down here. It's this leg right here. Pardon me. I labeled these wrong. This is CF right here, this is 4, and R here. So we have CF right here, and R. Those are the legs of our first large right triangle before we cut it with this blue line right here. Here's the hypotenuse, which is N. We can figure out N because we know what this length is. We already figured out the whole thing, and this cuts it in half, even though it doesn't look like it does. That's how the diagonals in the kite work. So we know what the length of this is, and we know this. So we can figure this one out. That's why I used N for knowable. But this part here, if we don't know what R is, we know this part, but it's hard to figure out what the heck this is. So if I just put in a question mark. It's N, this whole length here, that's PC, the hypotenuse of the large one. Well, it's N plus something that we don't know. But maybe we won't need to know this. Let's find out. Our next triangle, this is the larger one, which has a right triangle here. I mean, it's our second largest one. This is the large one. Here's the second. Of the two that are left, here's the larger, which now has the hypotenuse over here. Previously, FC was a leg. Now that we've cut this, FC is now the hypotenuse. It's up here. We have this side here. This is N. And then this, which of course is the same as this, EF over 2. Well, now we've got in just about everything except this triangle here. And that's this one, this little right triangle, and this, of course, is also a right angle. So this little leg here is our question mark. We don't know what this length is here. This, we know, is EF over 2. And this is R. Well, now we have some similar triangles, we can start laying out some ratios. And to make life easy for yourself, let's find some ratios that don't include the question marks. Let's find ratios that only involve numbers we can find, except for the R, of course, because that's the one we're looking for. Well, all we have to do is set up our ratios. They have to be the same. If these two triangles are the same, or similar, rather, then the ratio of hypotenuse, or hypoteni, has to be the same as the ratio of the corresponding legs, which in this case would mean that R over 4 was the same as EF over 2 over N. So I can go ahead and write that out. And that's over N, which is the same as multiplying by 1 over N. Just one snag at the moment. I haven't actually computed what N is, have I? So, let's try that. Well, if we do a little arithmetic here, we've got N squared right here, plus half of EF squared equals 4 squared. That's laid out right here, or with some rearranging, n squared equals 16 minus 1/4, that's 1/2 squared, times 192 over 9. That's the root of 192 squared right here, and 3 squared. Well, after some arithmetic, we get 16 minus 192 over 36, which reduces to 16 minus 16 over 3, or 32 over 3. That's n squared, so n is the square root of 32 over 3. Well, now we've got something. I have to give myself a little more room and write that r equals 4 times, and EF over 2. Well, that's the square root of 192 over 3, and we'll multiply that by 1/2. Okay, so far, what else do we need? 1 over n, which is the square root of 32 over 3, or we want over that, so that's square root of 3 over the square root of 32. So now we do a bunch more messy arithmetic. And when we rearrange this equation here, we get r equals 4 times EF over 2 times 1 over n. So we got 4 here, 1/2 of EF over 2, which is right here. Pardon me, it's 1/2 of EF, which is the same as EF over 2. And we divide by n, which is root 32 over root 3, or same as multiplying by 1 over n, so we just invert this, and multiply by root 3 over root 32. Yeah, it's kind of a mess. Everything of which we're taking the square root, since it's all multiplication and division, we can put it all inside one big square root. And if we do the arithmetic, 3 times 192 divided by 32 turns out to be 18. So we get 2 times the square root of 18, and that's going to be divided by 3. But that's the same as 2 times the square root of 2 times 9, right? Over 3, we can separate this as a square root of 2 times the square root of 9. Well, square root of 9 is 3. So this is just going to be, the 3's will cancel, and we'll end up with 2 times the square root of 2. And that's way back up here. That is, in fact, the radius up here, r, equals 2 times the square root of 2. That's a ways to go for an answer, if there's a simpler way to do it. It left me in the dust. This is the only way I could see to do it, except there's one more thing that I could show you that works for any triangle. When you want to find the radius of, it's called the incenter, I'll just throw it out and throw it out there, and you can see that it works. There's this formula that goes like this: s minus a times s minus b times s minus c, all divided by s, and you take the square root of the whole thing. Well, what the heck is s? Well, glad you asked. S is 1/2 a plus b plus c. What the heck is a, b, and c? these are the lengths of the three sides of the triangle. And S is the sum of those three sides divided by 2. So it's not the average of the three sides. That would be divided by 3. It's 1/2 of the sum. You could say it was 1/2 of the perimeter. What happens if we do that? Well, you remember up there, where were we? The sides were 12, 12, and 8. So, hope I don't make you seasick. We can substitute all that in. For instance, we get 12, 12, and 8 here is 24, and 8 is 32 divided by 2. S equals 16. Okay, so here we get 16 minus 12 times 16 minus 12 times 16 minus 8 divided by 16. And what's all that? Well, that's the same as 4 times 4 times 8 divided by 16. Oops, I was supposed to take the square root of that, wasn't I? There we go. And that's the square root of all that stuff. There's 16 down here. Well, 4 times 4 is 16, so we're left with the square root of 8, which is the square root of 2 times 4. 2 times, wow, that's a bad 2, isn't it? There we go. 2 times the square root of 2. And that's just what we got up here, isn't it? So if you enjoy memorizing formulas, you can remember this and not have to do all that work we just did with all those similar right triangles and figuring out lengths and ratios. But we don't actually know this formula yet, and I certainly am not going to derive it right now. But if you're, like I say, if you're into memorizing formulas, you can remember this one and use it to check your work. There's the formula, you plug the numbers in, and in a matter of seconds you have the same thing that took us 20 minutes to get. Here's one that's going to use a lot of the stuff that we learned in previous sections. For instance, what's the slope of line L? Well, let's take a look at this radius here. Now, that goes from 0, 0, that's the center of the circle, to minus 4, 3. So what's the slope of this radius? It's rise over run, which in a case like this is extremely easy to compute. It's minus 3 over 4. Actually 3 over minus 4, but same thing. Minus 3 over 4. That's the slope of the radius here. But we want L. What's the slope of L? It's perpendicular. That means it's the negative reciprocal. So we have that the slope of L is the negative reciprocal of this, which is 4 over 3. Okay. What about an equation for L? Yeah, give myself a little more room. That should be pretty easy, right? Now that we have the slope, and we definitely know one line on, pardon me, we definitely know one point on that line. So we can write that y, pardon me, knowing the point means we can write that 3, which is y, equals 4/3 x plus b is yet to be determined. But what's x in this case? Well, y is 3, x is 4. So let's substitute, pardon me, that's a minus 4, isn't it? Okay. When y is 3, x is minus 4. So what have we got? We've got 3 equals minus 16 over 3 plus b. We can add 16 over 3 to each side, and this would be like 3 over 3, right? So that's 19 over 3 equals b. I either need to stop doing things in my head or get a better head. This is 9 over 3, of course, not 3 over 3. Doped. So if I add 16 over 3 to 9 over 3, I think I would get 25 over 3. So over here, I just get b equals 25 over 3. That makes a lot more sense. So what we get for an equation is that, put it right here, y equals 4/3 x, that's the slope, we already know that part, and b turned out to be 25 over 3. What's the radius of c? Well, here's a radius I drew in right here. And this part here, well, we know that's 3, right? And this part, oh, the coordinate here is -4, but that means the distance from here to here is 4. So, here we have a right triangle. Here's our right angle here. 3, 4, remember? 3, 4, 5 is one of our standard triangles, one of our standard triples for a right triangle, 3, 4, 5. So we can just write down 5 right off the bat. Didn't even need to go 3 squared plus 4 squared is 25 and take the square root of 25. We shouldn't need to. By now we know 3, 4, 5 is the right triangle. Well, if this has a radius of 5, then this up here must also be where y equals 5, right? Distance from here to here, 5. Find the distance from L to the circle along the y-axis. That would be this distance here. Well, 25 over 3 is the y-intercept for our line. I'm going to subtract 5 from that. This is 25 over 3, this is 5, and that'll give us this distance right here. So that'll be easy. And let's do it right here. Yeah, let's do it down here. 25 over 3 minus, how about 15 over 3? I get it right this time. And that would be 10 over 3. That's the answer to this one here. 10 over 3. So, this was 4/3. Here we got 4/3 x, naturally, because that's the slope. Plus 25 over 3. That gives us the y-intercept. We got the radius pretty easy because we instantly spotted we had a 3, 4, 5 right triangle. And then the distance from the y-intercept to the circle is 10 over 3. Well, that's about it.